All right, so everyone, so welcome to another ROAR seminar for the spring 2022 semester. So for this week's seminar, we're going to invite the reinforcement learning team, which is part of our effort to build a open source ROAR, robot open autonomous racing software to share with the researchers and students and practitioners in the industry. So, and then all the students are including graduate students and undergrad students contributing to today's results. So without much ado, and I'm going to hand it over to the team, and then they can do a self-introduction. And I know that this is going to be a team presentation.
Okay, I'll go first. Hello, everyone. This is Reinforcement Learning team of ROAR. And first introduce our group members. It is Federico, Franco, Xuanmei, and Jingjing, and Armin. And here we will introduce to you about our current capstone work. Our goal is developing better autonomous driving algorithms for both reference hardware and simulated environments. We are focusing on simulated environments in color, which uses reinforcement learning strategies. And reinforcement learning covers many fields like the picture shows. It includes computer science, neuroscience, psychology, and all the fields contribute to the reinforcement learning. And now, what is reinforcement learning? And the four important parts in reinforcement learning is, the first one is the environment, the world our agent operates in. And the second one is state, the current situation the agent is in. And the next one is the reward. It is the feedback from the environment. And the last one is the action, how our agent interacts with the environment. And then reinforcement learning is an area of machine learning which concerned with how intelligent agents ought to take actions in an environment in order to maximize the notion of cumulative reward. And just like the picture shows, right? And then I think Armin and Federico will also cover the concepts of reinforcement learning in specific topics. And then let's pass to Armin to talk about the Atari problem.
Right. So the field of reinforcement learning really lit up with the Atari problem. So in 2013, we had Google's DeepMind Labs, which came out with their first algorithm called DQN, which was able to play Breakout. What was very interesting, though, was that not only was it able to play this game and get better than human level performance, it was able to exploit the game and figure out that, if you send the ball to the top, you can have the ball break multiple bricks. And so it was really interesting to see what reinforcement learning could do. This was like one of those first landmark movements that happened in this field. Next slide. So why Atari, right? And why are we talking about this when we want to solve the problem of autonomous driving, autonomous racing? So we chose to solve Atari first because Atari is a very good launchpad to understand how various reinforcement learning algorithms work. And it has very similar characteristics to the problem that we are trying to solve. And through this talk and maybe through future talks, we'll try and cover what those similarities are and how that has helped us. Notably, Atari has a very fast cycle time. So we can really test, train, and reconfigure and learn what these algorithms are doing really quickly, rather than trying to solve a bigger problem first. Next slide, please. So here's the game setting. So let's look at what the player sees, right? So when you're playing Breakout, what do you see? You see bricks, you see the board, you see the wall. And what can you control? You can control the board by either moving it left or right and trying to make sure that the ball never falls through the gaps. And well, how do you get a score? You get a score by hitting bricks, and different colored bricks have different point values. And the aim of the game is to clear the screen of all bricks. So that's what humans see, right? But what are we making the computer see when we try to solve the Atari problem? First of all, we downsize the image. So we have no room for the extra scores on top. for the RGB. We simply grayscale the image. And so you can see that the computer actually can see much less compared to us humans, because it cannot see the distinctions between the different colors. It's just a grayscale difference. And so basically it's a scaled down grayscale image. And what the actions that it can do is very similar to what we can do: move the board left or right by 1 pixel. And well, the reward again is the same thing, which is when it scores bricks. However, we don't only reward the agent with a brick when it actually hits a brick. We try, so there has to be a way that we can incentivize the agent to do actions that result in rewards in the future. So the way we do that is that based on a predicted future reward, we give the reward to the agent in the present, so that the agent is able to prioritize that and do actions which maximize future rewards. Okay, so Franco, do you want to jump in?
Oh, okay. So I will talk about how the RL agent learn the Atari. So step one, so the Atari, the model will just collect for different runs. So at the very beginning, there will only be random actions. And then so by this, we can jump to the step two. It can calculate the rewards towards the different runs. Can you jump to the next slide? Yes, and notice that the action toward a higher reward leads to a smaller loss. So we are designing the reward to be the same as the score earned in the Atari. So if the current action leads to a higher score in the future, then it will have a smaller loss. And then the step three. So after the model learns the reward, it will perform better actions. And then the random action will be reduced. And hopefully at the end, it will converge to a perfect action at the end to get the highest score. So Eddie, I think it is your part.
Right. So for the next step, we're going to talk about what is PPO, right? In 2017, OpenAI released this new class of reinforcement learning algorithms called proximal policy optimization. It was a lot easier to tune than a lot of the other state-of-the-art approaches. What was really interesting about it is just the way that it approached the aspect of calculating, what is our next best decision in a much more condensed and simpler way, while also, achieving our best possible outcome. So understanding the proximal policy function, and especially the loss function, if you look at here, in this slide, we have our loss calculation. And what's different about this versus traditional policy gradient functions is that we have a ratio of the old probability versus new probability. And what makes that different is that instead of just looking at all possible cases, you're now kind of condensing that into comparing it versus comparing the new expected outcome with the old expected outcome. And another thing about proximal PPO is that we're not only just looking across the entire data set, but we're clipping it so that we're not advancing any quickly or any faster than we really intend to. So we're really reducing how far we make those jumps, right? And that's huge because one of the big risks when you're doing these sorts of things is you end up learning way too quickly, and you make an assumption that doesn't allow you to converge. So by clipping how quickly we make these descents, we can reduce the risk of like overshooting and never converging. This is a much safer and much easier way to approach learning. So now let me talk about some of the hyperparameters that we want to tune here. There's quite a bit to talk about, but we picked just a handful that are really indicative, especially once you're like getting into the early stages of this, right? So first things first, the discount factor gamma, right? We like to think of it as like the foresight parameter. This parameter gamma indicates how far ahead into the future your model cares about its future reward, right? So if this value is very small, you're going to have a very myopic algorithm. It only cares about its immediate next step. So it's not going to think too far ahead, even if the next 3 steps are going to take it into something that could be a penalty. It's not going to care. And because of that, we typically want to keep this at a higher range. As you can see, we utilized a little bit towards the higher end of the spectrum of the recommended range of 0.8 to 0.9997. And this yielded the best results for us. A higher gamma value means it's looking further ahead, and it's going to say, okay, these actions might not reward me right now, but they're going to reward me later. And that's super useful. Learning rate is the exploration parameter, right? It's how quickly the agent can adapt to the problem, right? If you have a very complex problem, a great way of thinking about it is the learning rate allows you to go and explore a lot of different possibilities, right? This is great when you have no idea which way you want to go. However, over time, once you do have a model that's more or less making the correct decisions, you don't want it to make a radical guess, right? And so the learning rate is something that you may want to tune down after some time, right? Because what you're aiming for is like this Goldilocks zone. If you look at the image below, we've got examples of what a large learning rate and a small learning rate will do. A large learning rate may end up overshooting our local minima, which means you may never end up converging or finding what you're looking for, right? If the goal is to take a car from point A to point B, you may never end up getting there because you keep exploring areas behind you. But if you have a small learning rate, you'll be more confident that you'll arrive at your destination. So it's a better chance for converging, but it may take you very, very long, right? Because your model is going to take very few risks. So that's a good way of thinking about it. Next, some key values to analyze: entropy and episode reward. So entropy, we like to think about it as like our confidence parameter, how certain we are of our actions, right? And this value alone is super, super indicative of whether or not your model will converge at all, right? And that's very helpful when you are testing a bunch of new ideas and methods. You really want to pay attention to entropy, because if your entropy is not dropping, or in fact, it's like in some cases that we found it's going up, you're going to have a problem. It's going to lead to your model not converging, right? Because your agent is less and less certain about what it's doing correctly, right? You want to see this number go down. You can see here at the bottom where I have the approximate entropy graph. We ran a baseline test of the Atari problem, and this drop in the very beginning is exactly what you're looking for. This shows that the model is growing more certain about what it's doing, and it feels a lot more confident that it's making the right decisions. However, this green one right above is one where we set the gamma very low. Now, if you recall, gamma is how much we're looking into our future reward, right? So just as a test, we dropped the gamma to 0.7, which is well below the recommended range. And right away, you can see that the model never felt much more confident in what it was doing. And we also saw that in the reward. Over time, the reward for that particular run never got better. It stayed just as lost as it was in the beginning. So it's a very, very useful tool for you to know that what you're doing is correct, or at least has some promise. I should also caution that this is not an end-all be-all. Just because your model is more confident in what it's doing doesn't necessarily mean that you've achieved the best possible method, right? It's very useful to conduct multiple tests and observe all of the other parameters to see whether or not these results are really indicative of something great, or maybe it's something not so great. And then episode reward is just that your reward that you've collected over a single episode. How you define an episode is dependent on the problem. For Atari, it's going to be, 3 lives of the ball coming out in and out. And once you've expended all 3 of those lives, then the episode is over and you can calculate your total reward for those 3 lives. Here in this example, we just got some different examples of changes that we might have tried in order to increase our reward. The red is our baseline run with just nothing fancy. It's just as right out of the box, we did a test there. The blue line is without grayscaling. As mentioned earlier, the original problem, we remove all of the color. And so by adding the color back in, we can see a significant improvement just because, by adding RG and BN, that's 3 additional channels from which the model can learn from. And then at the very top there, you can see that we have a run where gamma is set to 0.975, which is a bit lower than the 0.99 we usually set it to. This was just a test to see if there were different gamma values with better results. And I think this is a really good example because while this gamma value did yield better immediate results, when we ran it a second time, we actually found that it performed significantly worse. And so this could be due to a wide assortment of things, but more often than not, it's just due to initialization. When you randomly initialize your weights and biases, you may or may not have just some runs that outperform others for no specific reason. So one thing you want to do to confirm anything that you do whenever you're playing with hyperparameter tuning is run it again and again and again, and make sure that you've got a consistently better agent than you did before. And then I also want to talk about weights and biases. This isn't something that we were we've very much been learning about this as we go, but this is a incredibly helpful tool for anyone that's exploring, training models and just looking at data and trying to analyze and see where do they want to go from there. It's not incredibly difficult to integrate into your system. In fact, it works with most systems that are already set up, like stable baselines or tensor. And you can use it to generate these incredibly in-depth reports. This is just a small snippet of all of the data that it can generate. It's really great for letting you see and compare multiple different runs, and just selecting them, letting you get a good picture of them side by side. Incredibly powerful tool. And this, as Professor Alan Yang was saying, this probably deserves its own seminar just to discuss all of the capabilities that this thing has available to us. And now I'd like to talk about frame skipping, which is specific to the Atari problem and how we then apply that to our situation, right? So if you think about Atari, you have a game that's executed in frames per second, right? Modern video games are executed at 60 to even 120 frames per second. But the Atari is roughly around 30 frames per second. It's not very fast, but it doesn't need to be. But why does this matter to us, right? Because every frame per second is how you interpret change in time, right? For our case, Carlo runs at a frame per second that we can actually modify. But this is important because how you perceive time is how you indicate to the agent what it needs to do or how it can react, right? So the more information we can give it about what happened in the past, the better or more educated decision it can make about the future. One of the problems with this, though, is now we have to pass in a lot of information in order to make sense of what's going on in the past. But frame skipping is a way that we can pass in a lot of information with very little data, right? So when we originally pass in this model, we eliminate the 3 channels as mentioned earlier. We grayscale it, and so now we have a single channel image that we're passing in. What frame skipping does is it eliminates every 3 frames for 4. So every 4th frame is the only one you're actually keeping and storing. All right, the other 3 frames are happening, but we don't care about them necessarily. We're not going to observe them, right? So on frame 1 through 4, we're going to eliminate 1, 2, and 3, and just keep 4, and so on and so forth, right? Now, why do we do this, and how does it help us, right? The great benefit about this is that we're able to see further into the past without necessarily storing all of that frame of information, right? It takes a lot longer for the model to process if we keep every single frame. And this is important because the higher the frame rate at which you run your model, then the less information you might get per second, right? In Atari, since it runs so low, we don't necessarily need the next 2 frames that are next to each other. The image is hardly going to change and the ball is hardly going to move in position over time. And so we're not getting very useful information from that. So we want to look further into the past. And by doing that, we add on more data. But by frame skipping, we can eliminate that and just focus on key moments in time. Now, what does that mean for our output, right? I know my team had a lot of trouble with understanding what this meant for how we output into the system, because as we all know, we are receiving the state and the reward from the environment. So what does that mean for the output of the environment? Well, for this case, what we can do is we're actually still outputting on the frames that you see crossed out, right? When you collect your 4 frames that, the first 4 frames that you're actually grabbing, you can still calculate an output that is individualized for each subsequent frame in time. So that means that frames, if we are not counting only the ones we keep, 1, 2, 3, and 4, we're going to be outputting on frame 5 and all frames between, right? This is an important thing to note because if you only, especially for Atari specifically, if you only were to output on frame 5 and you ignore the output on these blacked out frames, will end up happening is you might end up missing an input into the game, right? And that's a problem. It also means that your reaction time is much more limited, right? Where by frame skipping, we're already not able to react to the past within these 4 frames, but by individualizing every single output frame, we're able to create a sequence that says, okay, I'm going to turn right two times and then left once, right? As opposed to being stuck going a single direction just one time. And this is super critical to understand when you want to adapt this to any sort of game system or a virtual environment that runs on a time step. This is also useful when you want to apply this into the real, because how quickly your hardware is going to be able to pass in this information is going to make you have to train your system in a similar sort of environment. If your hardware can only do 30 frames per second or 8 frames per second, it doesn't do you a whole lot of good to train your model at a slower or higher frame rate. It helps to keep everything matched up so that the transition is smoother. All right, and now I'll hand it off to Franco to discuss ROAR.
Yeah, I think Xuan, you can start with talking about the game setting of ROAR.
Yeah, I will start talking about the game setting after learning a lot from Atari game. And here we just go back to our specific problem. We need to, based on the existing color simulated environment as shown in the picture, and our developed AI agent will need to completely autonomously control the RC vehicle to run a course around the simulated track of the Berkeley campus. The information in the color environment we can use, it is about the vehicle's location, speed, transform, and the environment data like occupancy grid map, we call it OGM in the next slides. And here are 2 options for us to choose. It is the traditional method of, it is called PID control. And here we choose to develop an end-to-end reinforcement learning model. This means our model will receive the information I mentioned above and about its surroundings and directly choose what action the car should take. And please move to the next slide. Here I will talk about the input we have. Here I would like to mention about the challenges we face dislike the PID controllers because in the past, the role competition was dominated by PID controllers, which are useful for finding optimal policies in continuous dynamic systems. And often these domains are also used as benchmarks for reinforcement learning. PID controllers only use the waypoints, we call it, to guide the car moving, while the RL agent need to handle multimodal inputs, which are more complicated for us. But our end-to-end reinforcement learning agent no longer needs to manually design or tune any parameters of the controller. It is our advantage here. And only through the rewards that has been set, the agent can learn how to drive by itself. We will describe how we design our rewards in the next slides. And yeah, let me pass to the Franco to talk about the rewards design.
Okay, so for the reward, it is very different from what usually it is. So by the game setting, it is only reward for you to drive as fast as possible to the goal. However, if we are only give reward to the time at the end, then it is hard for the model to learn at the very beginning, because just think about it. If you are doing random action, turning left and right, press some brake at some times, you cannot reach the end goal. Then you will never get the reward. So just like what we did in the OGM. So can you switch to the last slide? Yeah. So you can see on the right. So the first column is the wall we can see, and the second column is the way lines. So those are the lines that we add by ourselves. These are the subtasks that we want to add for the car. And whenever the car passes the way line, it will get a reward. And also we add a distribution on the way line, so that if the car cross the way line in the center, it will get a higher reward. And combine them together, you can see that on the fourth column, it is the map that combines the wall, the lines, which is the reward, and the car. So for the reward, also different from PID. PID usually just reward to drive as fast as possible to the target point. But we give reward to two things. The first one is the speed. We wanted to drive as fast as possible to the line, and then we are giving reward to cross the line. So in this case, the car will not only drive fast as possible, but in a right direction. And then we will give a penalty to the crush, because we don't want the car to bump into the wall, which will decrease the speed by a lot. And also we'll give penalty to being alive. So the car or the agent will know it should drive as quickly as possible to reach the end. Yes, and I will also talk about the action, which is the output of the agent. So usually when you are playing the game, you can press the W to increase the throttle. So but in our model, it will output the throttle with a range 0 to 1. So if the action is 0.5, it will jump to 0.5 directly. So it is pretty different from what you play. And so does the steering and braking. It has its own range. And it is also different from PID. So if you are having a PID model, the output is only the PID values, and then you need to calculate the throttle, steering, braking through the calculation. And the action is output for every frame. So every frame, the throttle, steering, and brake may change a lot. So here's our result. Eddie, can you show it to us?
Yep. So here we have it's a Tesla Model 3 running through the Berkeley minor map that we have. and it's running using our end-to-end model. So this wiggling behavior that you can see is just it learning the behavior of avoiding the walls and driving straight. At this point in our training, we've taught it to only control the steering, right? So the throttle is fixed at a reasonable speed and the brakes are off. So it can just learn and focus on handling its steering, but it does it quite well. It maintains itself in the middle of the track and can corner quite quickly. This is only after about 800,000 global time steps of training. And this took about 7 hours of time to train. And I'll hand it off to Aman for feature work.
Yeah, so as you can see in the video itself, right, like we are only controlling the steering and we aren't right now moving the throttle or the brake. And so that is a direction of future work. And I just to give people context about where this thing could go, I just want to let everyone know that this is very, very preliminary work at this moment. So the results that you saw on the previous screen, we just got those results in about 2 weeks ago. And so we ourselves are playing with it, trying to make it better, streamline it. You can see some wiggling behavior while the car is driving. We want to fix those things. But what are the large goals that we have to push this project forward, right? So the first thing is, of course, to tune our hyperparameters better. Right now, we are running a sweep as we speak. Our model is training. We are running a sweep over different hyperparameter settings to find ones that are better, that converge faster, result in better performance based on the different criteria that Eddie spoke about previously. The other thing that we're trying to do is generalize this model. So we want to add additional courses and maps. So there's the Berkeley major map coming up, which has many, many more turns and much harder turns. And so we hope to generalize the model much better. Another thing that we hope to add at some point is obstacles, right? So if the car encounters an obstacle, it's able to go around it. Another thing that would be really cool is spawn points, because having the car start at the same point can make it heavily dependent on where it starts. And so when we include random spawn points in our training, what that could allow us to do is generalize it better and make it less susceptible to failure when it starts at a bad location or any of the other things that we would throw its way. Something that Franco spoke about, and maybe I can expand on a little bit, is the optimal reward line generation, right? So right now, if you remember in the reward line slide, the reward lines are modeled as a Gaussian, and we give the car the highest reward if it passes right through the center of the reward line, right? So as anyone who's ever seen Formula One before knows that, it's not the most ideal strategy to pass through the center of the track all the time, right? You want to really optimize the race curve so that you can find the optimal trajectory to maintain speed and cover the lap in the fastest possible time. So the way you can do that is we can shift the Gaussian around. So you move the peak of the Gaussian around from left to right, and that is something that we will work on once we have this agent running stably across multiple tracks. And then finally, another cool direction this project is heading in is trying to adapt this to the row reference hardware. So we have the row team 1 with Adam and Sunisha, I think, who are on this call, and we are trying to see if we can adapt this hardware onto that reference, adapt this reinforcement learning algorithm onto that hardware so that we can have it actually run in the real world. So these are all very exciting different directions that this project could take, and yeah, you should stay tuned for updates.
All right, that's it for our presentation. Thank you all for tuning in.
Just a couple of helpful references in case anyone wants to go through any of the content we covered in more detail. These were really, really helpful in our understanding.
Yeah. If there's any questions, feel free to unmute yourself or go ahead and speak in the chat. We're watching that as well.
Okay, thank you, team. I have a few initial questions for, I guess, for the audience. Number one is that can you go to the reward page? for the driving. Can you go one page for previous page? So in here, how many channels do you have? And what is their dimension? And what are the values do you assign to represent the obstacles and the rewards?
Yeah, so this image on the right here is a great representation of what we are passing in versus what we're observing, right? So all the way on the right-hand side, this is the completed image of what we want the model to see, right? But this is not what the model is actually getting passed in. What it receives is 3 separate channels, one hosting just the borders, just the way lines, and just the vehicle itself, right? So there's 3 channels for a single step in time. As we discussed earlier, we do conduct frame skipping. And so we skip 4 frames and do 4 frames input in time. So we've got right here, frame 1, frame 2, frame 3, and frame 4. And these are all slightly different in position on the track over time. So
your first frame is being cut off. Is that?
Yeah. In this image, we wanted to focus in on the small details, how you can sort of see the gouge in here. But yes, it is a 3 channels, 4 frames in that channel.
And then what are their values?
Right. Everything is grayscaled from 0 to 1. And so we try to maintain that borders stay a solid 1, while the Gaussian, as you can see here, that ranges from, Franco, feel free to jump in, I believe, 0.3 to 0.8.
So the wall is 1.
Yes.
Okay, so it's 100% sure they are obstacles.
Yep.
Okay.
I'll also jump in here on one point. So another thing that we did is that we've adapted the same model structure that was used for Atari. And so the frame sizes are kept in line with what we observed Atari was doing. So 84 by 84 and 3 channels. And we had great success with this particular configuration in Atari, and which is why we spoke about Atari, right? Because that has driven a lot of the intuition that we have brought in to solve this problem.
Okay, so can you go to the final result, the demonstration of the, yeah, so here, there is a question about the simulation environment. So yeah, this is the Kala simulation. I don't know if anybody wants to say a little bit. For those people who notice that this actually is a 3D model of Berkeley campus. It's from Hearst to Gavey to Bancroft and then to Oxford. So our great students from the architecture department, they volunteered to build a 3D model of Berkeley. And then this server is a server client. This server is available to download. We can share with anyone who wants to drive. And because this is a racing, so there's no traffic lines, there's no pedestrians. And but I think by connecting multiple clients to the server, you could have multiple cars racing in the same environment. And the last thing, probably you guys see that, I don't know if you guys are feeling dizzy, so the single thing that the car is trying to optimize is speed. So it does not optimize the driver's comfort. So you guys can see it zigzagging left and right. So of course, for companies like Tesla or Cruise to do similar things, they're supposed to consider the behavior that more similar to human behavior, right? So this may be the safest car in the world, but other human drivers may think that you are crazy, right? So if you drive like that. So you need to have some degree of behavior that mimic the human behavior, so that you are allowed to drive on the road with other human drivers. So that part we did not, the team did not optimize to mimic the human behavior.
I think you bring up a really good point, and it's worth mentioning, is that this oscillation is, in some ways it seems like a consequence, but in other ways it's actually a method that the agent learned, right? We ran a test where we fixed the throttle all the way up to 100%. and said, okay, can the car still handle steering? Even with everything else set up the same way, can it handle steering with a higher speed? And a behavior that it exhibited after some, a good amount of training, I think about 1 million steps of training, is that it would oscillate back and forth in an attempt to slow itself down. So it would keep itself from hitting the walls, but it would oscillate back and forth a lot more exaggerated than this in order to keep its speed down, because it understood that if it had a slower speed, it could take the corner with more success.
Right. Another thing that you guys mentioned during the presentation is that because you are doing end-to-end, right? So the throttle and steering or brake are direct output from the output layer of the neural network, right? So if the neural network is going to set 0.7, it's going to directly jump to step 0.7. Versus a human driver, or you control the car in a keyboard, you have to tap, 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 right? So you have to gradually go from 0 to 0.7. Is that correct, right? For the neural network, you are able to directly set the throttle to 0.7 based on
Yes.
the
Right.
Yep.
And which is why you can see the steering as well, right? It's wildly swinging because a human can never make it turn that much, but the neural network can. It can just change from positive to negative instantly.
Okay, so there are some questions in the chat, so let's continue with that. I actually have another question. Can you go back to the reward, to the PPO formulation? Can you tell, for the sake of the audience, what is an advantage? Well, so actually, before that, I hope that everybody understand, the value function, which is the Q function, the Bellman equation. But the advantage is is an improvement of evaluating the Bellman equation, the value function. So what is an advantage? What is A?
Okay, so can you move to the previous slide? That's in
The previous slide,
your-
yeah. You need to explain that in the previous slide.
Right. So basically, the advantage is an estimate of, so the model does two things, right? It predicts based on what action it has taken so far, what its likely reward is going to be. And then it collects when it actually goes through, those number of time steps where it had predicted for, it actually collects what it actually observed versus what it predicted. And so the advantage is a measure of whether the model performed better than what it predicted or worse than. So a positive advantage you could think of is a measure of, is the model much better than its own prediction in that time step? And a negative advantage would sort of be a measure of it's much worse than what it predicted. And so the reason we have the advantage in this equation is that we want to make sure that if the model performs worse than what it predicted it would, that we sort of penalize it for those actions, right? And we try to avoid those actions because we want to maximize this. And in the case that the advantage is greater, so the model expected something but got much more, we want to move a lot more in that direction so that the model does receive that behavior. So that's the role that the advantage plays in this equation.
Right. So for those people who only have an introductory level of reinforcement learning, basically the value function or the Q function I mentioned is the absolute reward, right? And then the advantage, you can think about it as a delta, is whether you are getting more reward or you're getting less reward. So it is related to teaching a kid, right? So if you want to educate kids, it's not about their absolute performance, it's whether they improve their performance or they reduce their performance, right? So if your kids are already like A minus, is A, but one day they got A minus, you should, so that's treated as a penalty, right? But versus if you look at the absolute value, which is the review, the value function is already very high, right? From A to A minus, still very high. But you got a decrease in your reward. That means that you did something wrong. So you want to correct that. So the backpropagation to train to converge on the network parameters using the advantage seems to perform better than trying to only increasing the absolute value of the Q function. So that is one of the improvements after the initial paper from the DeepMind. Okay. All right. So then so that leads to a question Aaron asked. And how can if somebody want to look deeper into this, how can they learn about what is advantage, what is PPO? Are there any resources? OpenAI, papers?
Yeah, so if you really want to get into PPO and learn a little bit more about Advantage, this paper about from Toward Data Science about a graphic guide to implementing PPO for Atari games was pivotal to our success here. It does an extremely good job of kind of simplifying PPO and applying it into our problem here. Again, it's built for Atari, but they also have a Git that you can pull and start kind of playing around with these hyperparameters and get a better sense of what everything does and how it impacts. Another great aspect about it is that it really does a good job of going into detail about future reward and how it calculates the discounted factor. And that's really helpful for understanding why PPO is a slightly better model than, you know, some of the older work.
Right. Thank you. There's a question from Cameron asking if the jerky behavior is was reduced, will that lead to improvement in lap time? I guess that's the one of problem, right? So I think the earlier you guys consider penalizing the jitter, you know, the jerky behavior by if the vehicle is doing a lot of steering, potentially you can issue a penalty so that the car actually learns to drive straight. But the question was that will that lead to improving the lap time, or do you think that it will lead to penalty in getting slower lap time?
Does anyone want to jump in on that, or I can take it?
Yeah, sure.
Go ahead.
Yeah. Okay. So yeah, absolutely. If it you know, reduces that behavior, it definitely improves the lap time. In fact, that's what you will see if you know, were to pop in and look at what does a run like, or what does a run look like after it's been training for 2 hours versus 5 hours. You're going to see a lot more of that wild, you know, back and forth. But one important thing that I think, you know, should be noted is that there is an upper limit of how much we're able to reduce that, and that has to do again with this concept of frame skipping, right? If you are only able to react with like if you didn't do frame skipping and you only had every frame, then your reaction time is very quick, right? But if you skip a lot of frames and now you have, you know, 10 frames, say, that you skip before you can see a new update in your position and time, what that's going to do is it's going to basically cause, it's as if you were blinking while driving, right? So you can't necessarily react very quickly. And what that'll create is that exactly jerky behavior, because every time you open your eyes again, you see that your position's, you know, too far gone and you're overcorrecting it back and forth. So you really want to tune the frame skipping down to something where you can look far back enough, but also you have a quick enough reaction to the situation.
But there's a simpler way to, if you just want to go, is to reduce the jerky behavior. Of course, if you want the neural network to behave nicely, right? You want the neural network to behave like a human. You need to add penalty of, last couple of weeks ago we talked about unsportsmanship, right? So, or on human-like behavior, you want to penalize that. For example, if the delta of the steering is large, you penalize that. But however, there's a simpler way, which is outside the neural networks, that you can do smoothing, right? So if the current steering or throttle is certain level, and in the next frame, even if you jump frames, and then it's going to suddenly jump, a couple of 0.3, 0.4. But to get there, you can smooth from the current steering and throttle to the targeted steering and throttle. Right? So that is another way, like people, stepping on the gas or turning the wheels. It's gradual, right? So not sudden move. So the smoothing can be also implemented outside the neural network and outside the modifying the frame skipping scheme. Have you guys thought about that?
Yes, actually I have test on this. So for example, if the current steering is about 0.5 and the output of the action is about 0, I force it to only decrease by 0.2, so to 0.3 gradually. And I found that it is harder for the model to learn because it is trying to change the steering to a very low value because it want to maybe turn left or going straight, but it is not as it expect. So I would say, yes, this may cause a smoother behavior at the end, but the learning progress would be much longer.
Right. So you're saying that in order for the car to behave more human-like, it's I think it's more fundamental to address that as part of the network behavior rather than not following the network to do some filtering outside.
Yeah.
Okay. Right. Thank you. Are there any questions? Are there any more questions from the audience? Okay. All right. If there's yeah.
I think our emails are in the mail that was sent out. So if you have any questions that you come up with later, feel free to email any of us. We'll try and get back to you.
Yeah. Can you guys so if anybody who want to interact with any audience, can you type in your email address? And if anybody know me, and you can also email to me, especially for those people who want to request a follow-up talk about any particular things. For example, on the engineering side, how the network PPO is tuned, the tuning of network, and then accelerating the convergence. If anybody particularly interested about talking about this, send me an email, and we can coordinate with the team to do a follow-up discussion. Okay, I think Huazhou, we can stop the recording right now.